regular polygon. So, for example, this is regular pentagon, this is square, this is equilateral triangle, this is a pentagon, and so on. So every face of this polygon, regular pentagon, regular polygon. Those polyhedra are called Johnson-Zalgara polyhedra. Johnson-Zalgara, because Johnson-Zalgara found these. Here is only 20 or 30 things, but there are exactly 92 different kind of Johnson-Zalgara polyhedra. And you know the net of the polyhedra. So you make it flat and dissect this solid along the edge, okay, and to make connected part. That is called net or development of solid, okay, and at least one of the net of this polyhedra. This polyhedra is called tesseration polyhedra or tesserative polyhedra. Okay, and some English mathematician posed me that problem to me, and I solved that, and I determined 23 out of 92 polyhedra are tesserative. Same as this. This one is by 4 copies. I use 4 copies to tesserate like this. So tesseration means no gap. So if you have many copies, then you can continue and tesserate the place. Okay. This is a map of mathematics. The mathematical world is so big, enormously big, and number theory, algebra, and geometry analysis, and discrete math and operations research, numerical analysis, and so on. So many important topics. And my major is discrete mathematics. That is very small area, but shining. Shining is golden. Yep. Okay? Please look inside of this glass cases. There are 5 tesseration by polyhedra, and the first one is called truncated octahedron. The truncated octahedron, that is truncated octahedron is, you know, regular octahedron. And you cut off around the vertices. There are 6 vertices of octahedron. Okay? You cut off, truncate. Then you will get this. And you have you ever seen this solid or this shape in your daily life? This kind of. If you have never seen this, your cell is look like this, and you have 60 trillion truncated octahedron in your body, okay? And our soap bubble also look like this. Have you ever noticed? So if you wash the hand, then you have a lot of bubbles, and that look like this. Okay, and you know this one. This is very familiar. This is parallelepiped. Okay, and 3 pairs of parallel faces. And the special case of parallelepiped is a cuboid or a cube. Okay, box. And here is what do you call this? This one. Hexagonal prism. But little skewed. Okay, but even it is skewed, you can pack like this. Space. Okay, solid consists of 12 faces and 8 rhombuses and 4 hexagon on the side. So in total, 8 plus 4 equals 12 faces. Okay, and this one is called elongated rhombic dodecahedron. Elongated. Okay. That also tessellates the space, and this is rhombic dodecahedron. So many rhombuses. If you count, there are 12. So this is called rhombic dodecahedron. And a Russian crystallographer called Fedorov, he found there are only 5 space-filling solid in total, no more than 5. So only 5. If we restrict the polyhedra, must be convex. Okay, and the only translation, using translation. So it is not allowed to rotate 180 degrees. It is not allowed. Just translation. Only 5. And this is not important. I have written about 200 books so far here.
All of his publications.
Only 200. Okay. We are in Kagurazaka. This is very famous place, like Kyoto, Pontocho, Guam, and Kagurazaka. There are many geisha, still many geisha who are talented, very good in dancing, singing, okay, and always wearing kimono and something like that, okay. And so the Kagurazaka is famous for geisha town, but recently it will change to mass museum. Wow. Okay. So from square to parallel hexagon, we call this figure parallel hexagon because 3 pairs of parallel sides. So parallel hexagon. And this is, what is the name of this flower?
Flower.
Look like. But I meant then dandelion. Yes, you are right. Dandelion, and the shape of this is pentagon, like a house. Okay, and the dandelion changes to lion. Okay, and this I brought it to Guam last year, so you may remember that. This is Jin Akiyama, triangular face, okay, and change to a bird in the cage. And maybe you might be interested in how we dissect. Yeah, for example, from square to equilateral triangle. So if you are given a sheet of square paper and dissect it into finite number of pieces and rearrange them to make equilateral triangle. That must be very difficult problem. Last year I asked that question to my student. Among about 100 students, nobody answered, could not answer. So it must be very difficult. Okay? So we will cut like this. So, equilateral triangle here, and here, and here. And I found systematic method to find dissection line recently. For example, from hexagon to square, of course those two figure must have same area. Okay? And the dissection line is determined by superimposition of two tilings. One, the red one is a tiling by this hexagon. So please look at this. Okay, and the black one is a tiling of this square. Okay, and we superimpose appropriately. And by appropriately, I mean that every dissection pattern of every red rectangle, the pattern is same. If you superimpose like this, then look at this hexagon and this hexagon or this hexagon. Different, how to say, patterns. So this one and this one, the black the line locating differently, not homogeneously. So you have to superimpose that homogeneously like this. Then that will give you dissection line. So here also, this one is house pentagon. So blue one is a tiling by house pentagon, and I want to make it. I want to pentagon to square. Then I make the tiling by square and superimpose homogeneously. The resultant is homogeneous. For example, look at this black square. Then this one is a pattern inside. Okay, look like the capital Y on this bar. This is upside down, but same. Okay, so if you cut here like this, so according to this one, this will be guide how to cut. Okay, and quite same thing can be said to not only two-dimensional case. This is tiling, but also space tesseration. So here is a solid, and here is the other solid. Okay, and you cut this solid into several pieces and rearrange to make this one. Of course, the volume must be same. How to dissect? By plane. That is very difficult at the beginning, but now very easy. You make two tessellation. One by for example the solid A, and the other is a tessellation by solid B, and superimpose in your mind. Superimpose. Then you should cut like this. You will get. Okay? And not 4-dimensional, 5-dimensional space, every space we can generalize this result. Okay? So you are now an expert of geometry. Mathematics and art, who like painting or sculpture, okay? I also like paint, oil painting, or sculpture, or craft, medicine, architecture, those things. And so maybe you have seen this one. Katsushika Hokusai, Mount Fuji here. In Japanese, this series is called Fugaku 36. Fugaku means Mount Fuji. Okay? 36 is 36 scenes. And this is one of the 36. Okay? And Hokusai. And this is actually not printing. This is, how to say, wood print. Wood print.
Yeah.
Wood print. You carve the wood and print. Okay? And so this is big wave. And Mount Fuji is very small. And here is a boat. Okay? And although the Mount Fuji is drawn very small, everybody will watch Mount Fuji automatically because his design is mathematically. So here is a diagonal, and here is a quarter circle. Here is the center, and the radius is this, and you draw this curve, circle, a quarter circle, and the intersection, the Mount Fuji is located, the peak of Mount Fuji. And this big wave is falling down along this curve. And so automatically, oh yes, this big wave might swallow this boat. Okay? So they will watch and they will see the Mount Fuji will in their view side. Okay? And Hokusai said, the artworks or the picture which he drew before he learned mathematics was very stupid. He said, I didn't say, but he said in his biography, he wrote that. And after he learned math, his picture or wood print will be very famous and masterpiece. Yes. So he said that mathematics is important even in art. And this is Asia, Morris Asia, Dutch kappa printer, or yes, and the blue, no, white and brown hoses, and all hoses are identical pattern and repeated. Okay, And maybe you have seen this also, Piero. Piero, three color, yellow, red, blue. Okay? And they are all congruent. And he left many, many pictures like this, more than 1,000. And maybe you have seen at least one of them. Okay, something like this. And I wonder how he designed this kind of thing. So at the beginning it was very difficult, but finally I found it's quite easy. If you cut regular tetrahedron arbitrarily and make its net, then every net of regular tetrahedron tiles a place, tiles a plane, like this. So maybe in Guam, I showed you this kind of thing. This is, I have already cut. Here is small white regular tetrahedron. And here is something like this. Okay. And I have already cut. And I cut arbitrarily and make this flat. And then the resultant figure is something like this. And I made many copies like this. And that tesserate the plane.
Wow.
So many. For example, here Yumi made this. This is a firework. So she first made regular tetrahedron and cut arbitrarily. Then she got this kind of, like the skin of apple. She's here from tropical island. You have never seen apple? Apple, right? Apple skin. Okay, and take many copies of this one. Then it tesserate, and it look like firework. And here you will see small, tall tower. That is sky tree, we say. 600. Tomoko, do you know?
633. 34, I guess.
34?
Yeah.
So she said so. 634 meter. Very tall. And even, yeah, you can make a kanji. Kanji here. This is kotobuki, kind of congratulation. Congratulations to visit Tokyo. Tokyo University of Science. Okay? Kotobuki. I made from this. Here, regular tetrahedron, and I cut kotobuki. I peel and put. And I made one more copy with silver. Then that will fit, match. Okay? And maybe you have seen this kappa print. The title of this picture, kappa print, is Melancholia. Melancholy. Melancholy. And this is by Albrecht Dürer. Albrecht Dürer is Dutch or German, I'm not sure. Okay? And here is some guy. Here is a polygon, a polyhedron, and sphere, and gold is sleeping. Here is radar, and here is a Mahojin, magic square, 4 by 4. Yeah? And here is a rainbow. So here is an angel, small baby. Okay? And everybody is wondering, what does this kappa print mean? Then he is a mathematician, and he cannot solve problem. Okay, so he is annoying, but step by step he climb up. Then the future, your future, the golden future, brightful future is waiting for you. So do not give up mathematics, even if you feel it's very difficult. Continue, continue, continue. Then your future will be open. And what is this polyhedron? Polyhedron. I was interested, so I made quite same things here. It cost 25 yen. Yeah. Look at this. Crystal glass. Yeah? So maybe you know how to make this. So first we have parallel pipe, and you truncate the opposite diagonal vertices. Then as a resultant solid, we have 5 pentagons, congruent pentagon. 1, 2, 3, 4, 5, but no, 6 pentagon. And 2 equilateral triangles here. And what does this mean? Why this is drawn? Maybe I will give you a hint. You have seen this here. This one. You have seen this one. Here. Pentagram. This was the symbol mark of Pythagorean group. Pythagorean that is not a single person, that is a group. And their symbol mark is this. And here is a regular pentagon. And if you draw diagonal, then inside again the similar pentagon, and similar will appear. So this is called nested structure. And so maybe. So let me return the original topic. I let the technician make this. Take the point, gravity point of this pentagon or this equilateral triangle in the center of each face. And 2 points we join by an edge. If and only if these 2 faces has a common edge, then this point and this point we will join by an edge. Then inside you will see similar, quite similar polyhedron inside. And I could make up to here, but more nested structure. Maybe, but nobody know why he made this. Okay? So, my student will take you inside. Okay?